Hello and welcome to Otten Math. In this edition of Otten Math, we're going to talk about growth and decay, rational exponents, and radical notation. So two things we want to learn today. We want to be able to convert between radical and rational notation, and then we also want to know the basic growth and decay functions. Right, so rational form, we went over in the last class. Rational form has a base, and then a power, which is the numerator, and the index, which is the denominator. And in radical form, that translates to the root for the index, which is in the upper left portion above and to the left of the radicand and the radical sign. And then the power, which was the numerator in the rational form, upper right portion of the radical sign, outside of the radical sign, and again to the right. So both of these expressions request the same mathematical operation, and it is you're going to evaluate the 3 to the power of 2 and then find the third root of that value. And it actually doesn't matter which order you go in. You can take the third root of 3 and then raise that value to the second power, and you'll end up with the same answer. But really, two requests for the same operation stated in different ways mathematically. So rational form or rational notation and radical notation, you need to be able to convert between both notations and know what each request is asking you to accomplish. Right, so some things to remember. First, when you have a radicand that's underneath the radical sign, and you apply the index and the power, you're applying it to the entire value or quantity of the radicand underneath the radical sign. So the radical sign here, radical sign, so you're applying the power and the root to the entire radical sign, or entire quantity of the radicand. Now you also have to consider that in some cases this value is not stated, so there's no value here, and when that is the case, then the index is 2, and when there's nothing stated here, the index is 1. So that's why you see no value for an index when you take the square root of some value. All right, so I want you to go through these problems as classwork. We'll come back in a second. I'm going to pause, and then we'll go through the answers. All right, so we're converting between rational notation and radical notation. 3y to the 2/5. You can see that the power of 2/5 does not apply to the 3, just the y, so it's 3 times the 5th root of y squared. So again, placing the index here and the power just for this value to the upper right, or if it's only to a singular term, you can place that, excuse me, inside of the radical sign. Second problem, 3y to the 2/5. Now you have the quantity 3y squared and to the 5th root with an index of 5. Or you can write the values inside of the radical sign as the radicand is 9y squared with an index of 5. Next problem, number 3, a to the 4/7 times b to the negative 4/7. So you see we have two different bases, but a very similar exponent. So what we're going to do is we're going to change the exponent for b from negative 4/7 to 4/7, and that's also part of the simplification process. So we're going to rewrite this as 1 over b to the 4/7. Now I can say that a over b to the 4/7 is the same as the 7th root of a to the 4th times a to the 4th divided by b to the 4th. Excuse me. Last problem, a to the 1/10 times b to the negative 1/5. Now, if I wanted to combine the two terms with one radical sign, one value for the radicand, I need to have a common index. The common index needs to be a common denominator. So I'm going to change the exponent value from negative 1/5 to negative 2/10. and then I'm going to evaluate it by writing it as, or rewrite it as 1 over b to the 2/10. And then, so combining these two values together, I end up with a over b squared, and I'm taking the 10th root of that value. All right, so now we're going to go in the other direction. Now we're going to change radical expressions from rational or radical notation to rational notation. I'm going to pause here for a moment. Okay, so the first problem, the cubed root of 8x to the 7th, I can separate into the cubed root of 8 times the cubed root of x to the 7th. The cube root of 8 is 2, and then the cube root of x to the 7th is x to the 7 over 3. So you end up with 2 times x to the 7 over 3. Next problem, I can separate this problem into this 16 to the 3/4 times x to the 3/4. 16 to the 3/4 is 8. So 16, the 4th root of 16 is 2. 2 cubed is 8. And then 8 times x to the 3/4. Problem number 3. Again, I can separate out these individual values, 27 an integer, and then the two variables x and y. The cubed root of 27 is 3. And then x to the negative 6 over 3 is x to the negative 2, which is 1 over x squared. And then y to the 2/3. So 3y to the 2/3 divided by x squared is your answer. Problem number 4, x to the 1/4 times x to the 1/3 divided by x to the 1/6. I'm going to combine, I have two bases of the same different exponents, so I'm going to add the exponents together. X to the 1/4 times x to the 1/3 becomes 3/12 plus 4/12, or x to the 7/12. I'm going to change the denominator here because ultimately I'm going to subtract the denominator from the power of the denominator from the power of the numerator. So I change 1/6 to 2/12. 7/12 minus 2/12 leaves me with 5/12. So the value is x to the 5/12. All right, so one of the things that we're going to learn about in the next couple of chapters is logarithms, and one of the purposes of logarithms is to be able to find the value for a variable as an exponent. But in some cases, we don't need to use logs in order to find that value. We can use something called the process of equating exponents. But in order to equate exponents, we need to have a common base. So the equating exponents requires, again, that you have the same base. In this case, if b to the x is equal to b to the y, then we know that x is equal to y. So if I have a common base b and y, but the exponents are in different forms, I can relate them in such a way as to say that they're the same, and then solve for any variable that those exponents contain. So following with this example, I can rewrite 8 as 2 to the 3rd to have a common base, and then I can use the power of the powers property for exponents to rewrite 2 cubed to the power of x as 2 to the 3x. 2 to the 3x is equal to 2 to the 6th. Now the bases essentially fall away and become irrelevant. So I know that 3x is equal to 6. I solve for x. X is equal to 2. So I call this irrational and radical notation and exponents magic tricks. And this magic trick is just equating the base. All right, so I want you to solve this problem as classwork. I'll come back in a moment. So you can see that we can rewrite 9 as 3 squared. 3 squared to the power of x, using the power of the powers, becomes 3 to the 2x is equal to 3 to the 10th power. Equating the bases, or equating the exponents, I have 2x is equal to 10. Now solving for x, x is equal to 5. All right, so more classwork problems I want you to work on. I'm going to stop here. I want you to solve them and then check your work. All right, so for the first problem, we write 8 as 2 cubed. 2 cubed to the x is equal to 2 to the 7th times 2 squared to the 9th. Using the power of the powers becomes 2 to the 3x is equal to 2 to the 7th times 2 to the 18th. I have the same basis, so I'm going to add the exponents on the right-hand side. 2 to the 3x is equal to 2 to the 25th. Now I'm equating exponents because I have the same base. 3x is equal to 25. X is equal to 25/3. Second problem, I'm going to use a base of 3 in this case. I can rewrite 27 as 3 cubed, and I can rewrite 1 over 9 as 3 to the power of negative 2. So I'm always asking myself, if I just take a look at the values within parentheses, how can I rewrite 1 over 9 to have a base of 2? And after I've done that, are these two values the same? So we don't want to change the value, we just want to change the way that it looks. So the bases are the same between the two sides of the equation. So now I can use the power of the powers to rewrite the exponents and then equate the exponents. 3 minus 3x is equal to negative 4 plus 2x. Solving for x, I end up with x is equal to 7/5. Last problem, I'm going to rewrite 8 as 2 cubed. I have the same base, power of the powers. 3x minus 3 is equal to x plus 1. Solve for x, x is equal to 2. All right, so now I want to talk about basic growth and decay functions. So the basic growth function says that the ending value a sub t is equal to the initial value times 1 plus r, which is the rate of growth expressed as a decimal, to the power of t. Now t typically is number of years, but it can be any value of time: minutes, seconds, hours, months, quarters. Doesn't matter as long as you're consistent with that value. Typically it's going to be years. Now we need to have this value of 1 here. Otherwise, if we multiplied the growth rate, let's say we had 5% times the initial value, we would end up with 5% of the initial value. So we want to keep that initial value and then add 5% of that initial value to get the ending value. All right, so I have a problem here for you. We're going to work through it step by step. We're going to talk about Oprah's house in Montecito, California, which she purchased in 1993 for $245,000. And then she sold the house for $1.9 million last year. What's the annual rate, or in 2016, what's the annual rate of growth? All right, so we're going to fill out the values. The ending value a sub t is 1.9 million. A sub 0 is the initial value, 245,000. 1 times 1 plus r. We know that the time in years is 23 years. And now we're going to solve for r. So first thing we're going to do is we're going to divide both sides of the equation by 245,000. 1.9 million divided by 245,000 is 7.76. And then we're going to rewrite 1 plus r as x for now, because it's a little bit more difficult to extrapolate the 1 from the r in this case. We need to evaluate the 1 plus r first and then back out the value of r. So 7.76 is equal to x to the power of 23. I can take the 23rd root of both sides and end up with x is equal to 7.76. 7.76 to 1 over 23 is the same as 1.09317. 1 plus r is equal to that value, so I can find that r is equal to 0.09317, or 9.3%. So we see that Oprah's house appreciated at an annual rate of 9.3% per year over the 23-year period. All right, so last thing I want to talk about is a basic decay function. And the only difference between the two, decay and the growth function, is that now instead of a rate of growth, we have a rate of decay, and we account for that by subtracting that rate of decay from 1 instead of adding it to. So the only difference here is that this value, or this operation request, is a negative symbol instead of a positive symbol. All right, that's it for Otten Math, growth and decay and rational exponents. Catch us next time in the next edition of Otten Math.